In the today's session, we are going to discuss about one new model, that is digital signal processors. In that, first we will discuss digital signal processor architecture. Before discussing digital signal processor architecture, DSP architecture, first we will know about microprocessor and microcontroller architectures. Like microprocessors and microcontrollers, digital signal processors have special features that require operations such as FFT, fast Fourier transform, filtering, convolution, and correlation, and real sample based and block based processing. Therefore, digital signal processor use different dedicated hardware architecture. So first compare the architecture of general microprocessor with that of digital signal processor. The design of general microprocessors and microcontrollers is based on Van Neumann architecture. So whatever we are seeing on the screen, that is about general microprocessor based Van Neumann architecture. The design of general microprocessors and microcontrollers is based on the Van Neumann architectures. See, from this diagram we can see that this processor contains a single shared memory for programs and data. There is a single shared memory is there for program as well as for the data. A single bus for memory access. See, bus is there for memory access, and an arithmetic unit and program control unit. So the processor proceeds in a serial fashion in terms of fetching and execution of cycles. This means that the central processing unit fetches an instruction from memory and decodes it to figure out what operation to do. Then executes the instruction. The instruction has two parts, that is opcode and operand. The opcode specifies what the operation is, that is, it tells the CPU what to do. The function of opcode is it specifies which operation we have to do. Nothing but it tells the CPU to which operation it has to perform. Next one is operand. Operand informs the central processing unit, that is nothing but CPU, what data to operate on. The operand, once again I will repeat, the operand informs the CPU what data to operate on. So these instructions will modify memory input and output. So after an execution is completed, the cycles will resume for the next instruction. One an instruction or one instruction can be retrieved at a time. So because of that reason, the processor proceeds in a serial fashion. It causes most units to stay in a wait state. So from this we can conclude that Van Neumann architecture, it is a single memory. Okay, single shared memory is there. Now coming to the next one, that is digital signal processor based on the Harvard architecture. To accelerate the execution speed of a digital signal processors are designed based on the Harvard architecture. As shown in the figure, the digital signal processor has two separate memory, program memory and data memory. One is dedicated to program code, this one, and while other is dedicated to data code. Hence, to accommodate two memory spaces, two corresponding buses. See here, one address bus is there, two address buses are there. This address bus is meant for program memory, and this address bus is meant for data memory. Similarly, two data buses are there. One data bus is meant for program, and another data bus is meant for data. So, hence to accommodate two memory spaces, two corresponding address buses and two data buses are used. So in this way, program memory and data memory have their own connections to the program memory and data memory bus respectively. So this means Harvard processor, this Harvard architecture can fetch the program instruction and data in parallel at the same time. So comparing with the Van Neumann architecture, there is a in the Van Neumann architecture single and shared memory is there. That is only one address bus, only one data bus is there. It functions in serial fashion like a chain. But coming to the Harvard architecture, it operates parallelly. Nothing but execution of the program instruction and data are performing at the same time. So let us compare these instructions. Nothing but let us compare these two architectures uh, with the help of cycles. Before discussing, one more thing we can observe here, comparing with previous slide and this slide. See, in this slide, program control unit is there, arithmetic unit is there, and only one memory, that is program and data memory. Both are shared in a single memory, and only one address bus, only one data bus is there, and remaining part is IO devices. And coming to the hardware architecture, we can see uh, multiplier and accumulator, one more shift unit, and address generator. So these regarding these hardware units we'll discuss in the next slide. So from comparison of these two architectures, we can see some points. We can list out some points as the first cycle obtains the upcode from the memory. See here, this is we are going to distinguish these two architectures with help of cycles, execution cycles. Okay, first one, the execution cycle based on the Van Neumann architecture. The fetch cycle obtains the upcode from the memory, and the control unit will decode the instruction to determine the operation. Next is execution. That is, next is execute cycle. It is based on the decoded information. Execution will modify the content of the register or the memory. Once this is completed, the process will fetch the next instruction and continues. The process continues like this manner. So the processor operates one instruction at a time in a serial fashion. To improve the speed of process operation, Harvard architecture below this one takes the advantages of a common digital signal processor in which register holds the filter coefficients while other register holds data. So we are making use of two registers. One is for data and one is for program. So this one is we can see with the help of diagram. See second diagram. The execute cycle and fetch cycles are overlapped each other. We can see in the second diagram, execute cycle and fetch cycle, both the cycles are overlapped on each other. So this is called as pipelining operation. The digital signal processor performs the one execution cycle while also fetching the next instruction to be executed. Nothing but it means execute cycle means it is the execution of first data. While executing the first data, parallelly it will fetch the next instruction. I will repeat once again. Fetch and execute. See, this is cycle. First cycle. Oh, sorry. This is execute cycle. Fetch and execute. It is about the one program, one instruction. If we are executing the first instruction, in meantime, it will fetch the next instruction parallelly. Because of that reason, this operation is called as pipeline operation. So the digital signal processor performs one execution cycle here while also fetching the next instruction to be executed. Hence, the processing speed is dramatically increased. Because of that reason, we can say that the Harvard architecture is prepared for all digital signal processor due to the requirements of most DSP algorithms such as filtering, convolution, correlation, FFT. FFT means fast Fourier transform. So in case of fast Fourier transform, which needs repetitive arithmetic operations, including multiplications, additions, memory access, and heavy data flow through the CPU. Because of that reason, Harvard architecture is prepared for the digital signal processor. It is about whatever we discussed till now. It is about a general microprocessor with Van Neumann architecture, and next one is dedicated processor, that is a digital signal processor with the hardware architecture and respective cycles, execution cycles we discussed. Now, in the previous slide, we observed that address generator is there and multiplier and accumulator shifter unit is there. Regarding these three, we will discuss separately. That is, those are called, those are discussing those topics we are going to discuss with the heading digital signal processor hardware units. First one, MAC. MAC means multiplier and accumulator. In short, we are telling it as MAC. As compared with the general microprocessor based on the Van Neumann architecture, the digital signal processor uses the MAC. MAC means multiplier and accumulator. It is a special hardware unit for enhancing the speed of digital filtering. This dedicated hardware and the corresponding instruction is generally referred as MAC operation. MAC is a shortcut. See, MAC means in a MAC, M stands multiplier, AC stands for accumulator. So we will see the basic structure of MAC here. In this slide, we are seeing basic structure of MAC. Here, how it works, we will see. This is a typical hardware. The multiplier has a pair of input registers. X register, see this is the multiplier unit. This multiplier unit has two inputs, X register and Y register. Okay. Each register holding 16-bit input. Each register is holding 16-bit input and it is given to the multiplier. So once again, I'll repeat, multiplier is a block. It has two inputs, that is X register and Y register. Those two registers are giving 16-bit input data to the multiplier. The result of the multiplication, after multiplying these two values, the result of the multiplication is accumulated in the 32-bit accumulator. So once again, I'll repeat, after multiplying these two values, those values are going to accumulate in the accumulator. It is a 32-bit accumulator unit. So the result register holds the double precision data from the accumulator. It is about the multiplier and accumulator, MAC. Next one is shifter. So what is the function of shifters? In digital filtering, to prevent overflow, a scaling operation, this point we have to remember, a scaling operation is required. The function of shifter is scaling operation. A sample scaling down operation shifts the data to the right side. Remember, scaling down means shifting the data to the right, while scaling up means shifting the data to the left. Scaling down, shift to the right, scaling up, shift to the left. So it is about shifters. Next one is address generators. What is the function of address generators? The digital signal processor generates addresses for each data on the data buffer to be processed. Okay. So it operates in the circular fashion. It operates in the circular fashion. So in circular buffering, a pointer is there. See, this one is indicates pointer. A pointer is used and always points to the newest data sample. Okay. After next sample is obtained from ADC, analog to digital converter, the data will be placed at the location of x of n minus 7. Once I'll repeat, after the next sample is obtained from ADC, the data will be placed at the location of x of n minus 7. Okay. And the oldest sample is pushed out. This is the oldest sample. It is pushed out. Okay. Thus, the location x of n minus 7 becomes the location for the current sample. See, likewise, this will be the oldest. It will push out, and x of n minus 7 will be come to here. This is the new sample. It acts as a current sample. Hence, thus the location for x of n minus 7 becomes the location for the current sample. Okay. The original location. This is the original location, correct? Before this is the original location. The original location for x of n becomes the location for the past sample of x of n minus 1. Nothing but this will go to here. This x of n will go to here. X of n minus 7 will go to here. Circularly shifting. Okay. The process continues according to the mechanism. So for each new data sample, only one location on the circular buffer needs to be updated. So the circular buffer acts like a first in first out manner. FIFO, first in first out buffer. Okay. We will see this with one more diagram. Okay. In this diagram, we can see there is a data flow to the ADC, analog to digital converter, A, B, C, D, like this data flow, A, B, C, D, E, F, G, H, like that, and a circular buffer. This is circular buffer, and it is the FIFO. Let us see how it operates. The pointer here, the pointer specify the current data of D. This is the current data. In the circular buffer, this pointer indicates the D is the current data. And the equivalent FIFO. So if you are mentioning this circular buffer in the FIFO order means this is the current one. First in, first out. Okay. D, it will acts as a current data. And before this, before D, C is the current data that is pushed to the next location. Okay. D followed by C followed by B followed by A. So D, C, B, A, FIFO. Okay. Next. The pointer. Okay. Next. When E becomes, see now earlier case D is the current data. When E becomes in and the middle, okay, the circular buffer will change. The circular buffer will change the pointer to the next position, that is E, and update old A. A is moved away. So what happens? D will go to C position, C will go to the B position, and A is eliminated. Because here E acts as a current data, and this is pushed to here, C is pushed to here, B is pushed here, and A is eliminated out. Okay, like that. So the circular buffer will change the pointer to the next position and update old A within a new data E. It costs the pointer only one movement to update one data in one step. However, on the right side, see, we can see in the right side, the people has to move each of the data down to let in the new. Okay, this is about circular buffer and PIPO order. So for this PIPO, it takes 4 data moments. We are seeing it takes 1, 2, 3, 4. It takes 4 data moments. So in the bottom, we can see the each and every operations. This is about first one, second one, third one. Okay, the incoming data F. Next one, first incoming data is E. Next one is F. Now the pointer is here, and what happens? In place of D, in place of E, F is coming, and E is pushed here, D is pushed here, C is pushed here. Okay, so the incoming data F for both the circular buffer and the PIPO continues. So we can observe these movements. So like FIR filters, like finite impulse response filtering, the data buffer size can reach several hundreds. Hence, using the circular buffer will significantly enhance the processing speed. If you are recalling the points means a simple thing. Initially, the pointer is pointing here. This is the current data. This current data is moved here. So if D is the current data, coming to PIPO order, D is the current first location, followed by second fast, C, followed by previous fast, B, followed by A. Next, if one more data is entering, that is E, and the pointer is pointing here, what happens? E will goes to the current location, current data, and previous data is D, and previous to that C, and previous to that 3. Similarly, one more data is entering, that is F. F acts as a current location, and pointer is pointing here, and F will be the current data in the PIPO. Previous data is E, previous data is D, and previous to that C. It is circular, it is PIPO order. So today's class, today's session, we discussed about Van Neumann architecture, Harvard architecture, and comparison of these two architectures with the cycles, as well as we discussed some hardware parts of Harvard architectures. Recalling the points in the Van Neumann architecture, only one single memory is there that is shared between the program and data. Only one address bus and only one data bus is there, and it acts in a serial fashion. It functions in a serial fashion. And coming to the Harvard architecture, it has separate memory for the program and data. Similarly, it has two address buses. One is meant for program memory and other is meant for data memory. And it also has two data buses. One is meant for program memory and other is meant for data memory. This operation is called as nothing but executing of first instruction. See, we can see here. This is about the execution cycle of Van Neumann architecture. A fetch cycle. This is fetch cycle. This is execute cycle. Fetch and execute cycles will complete execution of one instruction. After executing first instruction, it will fetch the next instruction. So because of that reason, we can say it is a serial fashion execution is there. And coming to the uh, execution cycle of Harvard architecture, see here we can see it is the first cycle of first instruction. While executing the first instruction, parallelly it will fetch the next instruction to be executed. So this operation is called as pipeline operation. Because of that reason, we can see that with a diagram as well as cycles, the Harvard architecture has two separate memories for program and data, two separate address buses for program and data. Similarly, two separate data buses for the program memory as well as data memory. Okay, and this operation is called as pipelining operation because execution of first instruction parallelly will test the next instruction to be execute. So these are the points regarding about comparison between Van Neumann architecture, Harvard architecture. Now some special cases of special parts of DSP units, that is a digital signal processor hardware units. Mac nothing but, yeah, in a Mac, M stands for multiplier, AC stands for accumulator. So multiplier, see the title itself indicates multiplication operation is there. We have to perform multiplication operation. So how it is going to perform multiplication operation? The From this diagram we can see multiplier is a block. It takes two inputs. It holds two inputs, that is X registers and Y registers. X register has 16-bit data as well as Y register has 16-bit data. After multiplying these two values, that the result of multiplication is stored, or the result of multiplication is accumulated in the accumulator block. It is of size 32-bit. If double precision is there, that is held by result register. And address generators, as I told, now the data point is pointing in this location. X of n acts as a current location. If one more new data is coming, then x of n minus will go to x of n position, and x of n will go to the x of n minus 1 position. Like that, circularly we are shifting, buffering. Next one is the same operation is indicated, illustrated with the help of some examples. This is about today's session.